Okay, so some of you are still here. So the plan for today is, main goal for today is to prove Bourgain's booster theorem, which we stated yesterday. And the way we're going to do it is via this global hypercontractivity, whose meaning I will explain. Okay, but let us first remind ourselves of the goal, which is this Bourgain's booster theorem. Okay, so we discussed yesterday monotone graph properties. So this is a monotone property. Yeah. So as it turns out, we don't actually need it to be a graph property. It could be any property. It doesn't have to be symmetric in any way. Proof will just work anyway. And we said that you can look at the critical probability as sometimes I call it P hat, but maybe sometimes also write PC. So this is a probability that the graph property or the property holds with probability 1/2 exactly. And we can look at the window of the threshold. So one way to define it is look at the probabilities P1/3 and P2/3, which are the probabilities where this property holds with probability 1/3 and 2/3. So these numbers are arbitrary. I mean, if you change them, it won't make any difference. Okay, so we say that the property is a coarse threshold if the distance between P1/3 and P2/3 is comparable to P1/2. An example, the property of containing 10 triangles. And otherwise, it's sharp. And you can make it quantitative, like, okay, so if the gap is constant, we say that it's coarse, but you can also ask what happens if the gap is log n, and so on. Okay, so if we know for some reason that the threshold is sharp, then it's easier to locate it. Okay, because if you found a probability P where the probability that the property holds is not super close to 0 or to 1, then you're basically at the threshold. Yeah, this is the idea. So we would like some criteria that will imply that a property has a sharp threshold. So these criteria are known as sharp threshold theorems. And the way they are formulated is if the property is coarse, then blah. Okay, and if you can show that blah doesn't hold, then you know that the property has a sharp threshold. Okay, so the most useful of these properties is this Bourgain-Bousslet theorem, which appears in an appendix to a paper of Friswood. And it states, so let that be the characteristic function of monotone property. It doesn't have to be a graph property with a coarse threshold. And let's assume that the critical probability is small, it's little o 1. And we'll see where it comes up in the proof. Then there exists some probability in this threshold window, and the set H on a constant number of size order 1. Okay, so this order 1 here, it depends on the coarseness of the threshold. Okay. This set H could depend on n, but the size is bounded uniformly. Okay, so that if you fix the coordinates in H to 1, then this boosts the probability of the property to hold by some constant. Then yesterday someone asked, like, can we choose H arbitrarily or so we will see that the proof will give us an H. And let's say your property is a graph property, and let's say that H is a triangle, then because it's a graph property, then all triangles look the same. So you just care about the isomorphism type of H and not about the names of the vertices. Yeah, but it's important that it's in a fixed location. Yeah, if it's not in a fixed location, then the theorem is false. Okay, so this is the theorem, and Bourgain had a proof, which I'm probably I looked at it, but you know, we can't get much. Cannot get much out of this proofs by Bourgain. It's this long calculation. I mean, not so long, it's short calculation, and you get the theorem, but you don't see what's going on. But with this new technique of global hyperconnectivity, you can actually give a proof where you are able to see what's going on. So this is what I'm going to present today. Okay, so what we saw yesterday. So if is P 2/3 minus P 1/3 order 1, then there exists a P in order P hat. Then there exists a P inside P 1/3, 1 P 2/3, so that the influence of F with respect to mu P is order 1. Okay, so that's what we saw yesterday, this Russo-Margulis formula, proximate 0-1 law. Okay, so this was this calculation that I did using this coupling, but you can also do using the chain rule for the derivative. It gives you a formula, and you can interpret the formula in terms of influence once you define influence. And the way we defined influence was by using the same Fourier formulas. Okay, now there is a theorem which I stated yesterday. I'm not going to write it again today. This is Friedgut's Junta theorem. Okay, and it holds with respect to mu p when p is constant. So for example, the original setting was just 0,1 to the n with respect to the uniform measure. So we have a function from 0,1 to the n to 0,1, and it has a small influence. Let's say constant influence. Then the Friedgut Junta theorem states that it's close to a junta, where a junta, a Boolean junta, or a junta is a function that depends on the constant number of variables. Okay, so if this theorem was true in general for arbitrary p, then it would imply that any graph property or any property with a coarse threshold would be close to a junta. But the property of containing a triangle has a coarse threshold, but it's not close to a junta. Right? It really depends on all the vertices. Okay, so I didn't show you the proof of Friedgut's Junta theorem, but it's very similar to the proof of the KKL theorem. And the crucial thing that you need to use is this bound on the the level D inequality applied to the LIFs. Okay, yeah.
Sorry, I'm a bit lost from the beginning, but f is as far as I understood, f is a characteristic function of some subset of hypercube.
Right.
And h is also a subset of hypercube.
No, h is a subset of the numbers 1 to n. Or if it's a graph property, it's a collection of edges.
And then what do we mean by the x or characteristic of h?
Right, so here or is supposed to be the maximum function, the pointwise maximum. So basically this is the same as x, where we set the coordinates in h to 1.
So h is a set of coordinates.
H is a subset of n. So the function f is from 0,1 to the n to 0,1. And h is a subset of 1 to n. If it's a graph property, then this n is n choose 2.
Thank you.
Okay, so I'm switching from graph properties to arbitrary properties because the graphical case has no advantage to us. Okay, sometimes we're in the situations where being a graph property is useful. Okay, and in most situations, it's enough to know that the function is what's known as transitive symmetric, which means essentially that all the coordinates look the same. Okay, so the formal definition that it's invariant under some transitive permutation group, but it just means, for example, that all the influences are the same and so on. So this is how we usually take advantage of graph properties. And there's also a paper of Boolean and Kalai where they use something else, but nobody understands this paper. So yeah, so hopefully now it's a little bit clearer. So maybe I'll also change the name from H to S. So we don't think of it as a collection of edges, it's just a set of coordinates. If F is a graph property, then this S will be a subgraph H, but doesn't have to be the case. Okay, so is the statement now clear? Okay, so back to the story. Yeah, so we didn't show the proof of Friedrichs-Junta theorem, but you'll have to trust me, it's very similar to the proof of the KKL theorem, and it uses this level D inequality, which in turn relies on hypercontractivity. So if anything fails, then it's probably this hypercontractivity. Okay, and let's see why this is the case. So suppose that we had T log F4 is at most F2 with respect to mu P. Okay, and this law, it could depend on P. Yeah, so maybe it's a bit unfortunate, so I'll try to write them so that you can easily distinguish them, but they do look slightly the same. Yeah. I guess, yeah, it's not so related, but this sort of thing happens in many writing systems, and then you start adding dots to distinguish between things. So I'm just adding this thing instead of a dot. Okay, so this implies that if, or rather, F4 is at most rho to the minus degree of F times F2. Okay, so we've seen that during the proof of the KKL theorem. Okay, so first you prove this level D inequality, which follows directly from this hypercontractivity. And then there was this additional calculation where we got this. Well, I guess no, this followed directly from hypercontractivity, and then the level D inequality followed from this. Yeah, so this just follows directly. Okay, and yeah, let's see what we get. So we do everything with respect to mu P. So we take F to be the x1 function. Okay, so what is F4? This is expectation of F to the 4, okay, 1 to the 4 to the 1/4. So this is P to the 1/4. And also an F2, similarly, this is expectation of x1 squared square root, which is P square root. Okay, and yeah, this thing is a lot larger than this thing. Okay, so this implies that if this thing falls, then rho has to be very small, most like P to the 1/4. Yeah, all this would be. Okay, so if we take this test function x1, then we see that if hyperconductivity were true, then the noise rate would have to be very close to 0. Okay, so I mean, if P is constant, then this number, instead of being this 1 over square root 3, it would be something else maybe, but it's plausible that it's a constant, and indeed it is a constant. But when P is small, then this noise rate has to be very small. And this noise rate, it shows up, or rather its inverse, it shows up in all of the theorems. Okay, so I mean, you have to do the calculation, but you'll see that you will be able to prove an analog of Friedrichs-Junta theorem, that there will be like 1 over some power of 1 over P around, and it will make this result useless. Okay, you'll get something like your function is n epsilon close to Junta, which is not very helpful. Yeah, so it's something which is actually true, but not helpful. Okay, so this hyperconductivity, it doesn't hold unless you choose a noise rate very small, which makes it kind of not so useful. So like if you try to do something like this, then you will get these theorems where, let's say, the size of n dependent on n. So maybe you'll get that there's a set S of size n, okay, it's not so helpful. And similarly, if you take a function like this, then now this will be p squared to the 1/4. You get the same issue. Okay, so this is where things stood for many, many years. So you were just not able to use hyperconductivity when p was super small, and you had to do other stuff. So actually, I can't tell you what Boolean used instead. I don't remember. In some of my papers, you do some reduction to the case of the unbiased Boolean cube in some way, and that's how you are able to get something. Yeah, but it was a problem. And finally, now Nikit came up with a solution. So it is possible to come up with some hypercontractive inequality, which is meaningful. Okay, and it makes sense for all p with the constant noise rate. Okay, so I'm not going to formulate it for you, but we're going to see some kind of corollary, which is what we actually are going to use. And the idea is that you cannot expect hyperconductivity to hold in general because of these bad functions. But what if your function was very different from these functions? Okay, so there's a way to measure this. Okay, so if you recall, we defined yesterday this DIF. So yesterday we defined DI of f, which was f when you fix I to 1 minus f when you fix I to 0, which is also the derivative with respect to xi of f, of the Fourier expansion of f. Okay, so this came out yesterday in the when we try to understand this Wilson-Margulis formula in terms of the Fourier expansion of f. Okay, and similarly, you can define the S of f for subset f. So let's say that S is I1 up to IK, then this is just DI1, DI2, DIK, Again, and the order in which we apply these things, it doesn't matter. Okay, you can see it, for example, from this definition. Okay, so we know that derivatives commute. You can see it from the Fourier expansion, which, if you recall, up to some scaling factor, it would just consider only the Fourier coefficients that contain the coordinate, and then we remove it from them. So if we do it, it doesn't matter in which order we do it. And you can also see it from this kind of formula. So I'm writing it because we will need it later. So if you look at, let's say, di dj f, then what you will get is f of x ij gets 1, 1. And it's f of x ij 1, 0. Zero, 1. So some kind of inclusion exclusion. Okay, and you prove this by induction, and you can see that this formula doesn't depend on the order. Okay, so whichever way you prefer. Okay, so now we defined it. Okay, so now I will say definition F is beta global if DSF L2 norm is at most beta for all S. Okay, and in the applications, F will always have a bounded degree. Okay, but this definition makes sense for any F. Okay, so here are some examples of functions which are not global. X1. Okay, so if you look at D1 X1, you got just one. Okay, which is something huge. So we want a function, we say that it's global if it's beta global for some beta which is small. Yeah, so X1 is not beta global because I mean you have to choose beta equal to 1, which is large. X1, X2 is also only one global because if you take S to be the set 1, 2, then again you will get 1. Okay, so if a function is beta global where beta is small, then it's far away from these functions, and then it's conceivable that you will be able to prove some form of hyperconjectivity. Okay, so what global hyperconjectivity states, this is a theorem, global hyperconjectivity. So there exists a law independent of P such that for all P and for all beta, if F is beta global, then P or F4 is at most the mean of beta times F2. Okay, so this should remind you of the usual hyperconjectivity, only you also have this beta here. Okay, so this is the only difference. So kind of what's happening here is that if your function is beta global for some beta which is small, then you sort of have hyperconjectivity and you can try to do the proof as usual. So the only reason that these proofs they fail is because the function is not so global. Okay, so if your function is, if it's beta global for small beta, then we think of it as like pseudo-random. And pseudo-random functions are well behaved. Okay, for example, they satisfy this kind of inequality, which implies, I don't know, concentration, level D inequality, whatever you want.
So is it qualitatively the same as saying F cannot be expressed by few characters?
I don't think so. Yeah, so usually I guess we think of F as having low degree, and then it's somewhat sparse. So it's like saying that all of its Fourier coefficients are small in some aggregate sense. Yeah. Okay, so we haven't discussed this this other major result in Boolean functions called the invariance principle, but let's take another example. So you know about the central limit theorem. Okay, so the central limit theorem, you take a sum of IID random variables, and it converges after you normalize it to Gaussian. Now, let's imagine that we take a weighted sum of these, let's say it's Bernoulli's, a weighted sum of Bernoulli halves. So if the weights are all the same, then you will get a Gaussian distribution. But let's say that I take x1 plus 0 times x2 plus 0 times x3, plus 0 times xn. Then this won't look like a Gaussian. But if I take a sum and all of the coefficients are small, okay, here they need to be small with respect to the sum of their squares. Okay, then you do have a kind of a central limit theorem. So this is the Berry-Essien theorem. Okay, so there is the condition. Something like this is true in general for a function of arbitrary constant degree. And the condition for this to look like Gaussian in some sense is that all of the influences are small. Okay, so if you compare the behavior of the Boolean cube to Gaussian space, whatever that means, then your notion of pseudo-randomness is that all of the influences have to be small. This is the classical stuff, which I haven't described, but it's something classical. And here you need not only the influences, but also like the higher order influences. And the reason is these examples. Okay, so I'm not sure if it was understandable. This is also related to regularity lemmas. So if you've ever seen the proof of the triangle removal lemma using regularity lemma, then there's some kind of notion of pseudo-randomness that comes up there that allows you to prove the counting lemma for triangles. Okay, so this is the notion of pseudo-randomness that works for that domain. And here the notion of pseudo-randomness that is relevant is this. Okay, so sometimes you can combine this global hyperconductivity with some kind of regularity lemma, which is geared toward this notion of pseudo-randomness and get somewhere. Okay, so actually a lot of the applications to external combinatorics use this framework, where you use some regularity lemma, where your notion of a regular, in this case it's a leaf, is being beta global for small beta. Yeah, I won't have time to explain any of this, but if you look at the literature, if you're brave enough to look at these very long papers, then that's what they do. Okay, now we can circle back. Yeah, so this is this global hyperconductivity. It's called global hyperconductivity because it only holds for global functions. But the way that you prove it, you prove some inequality which holds for all functions, and then you deduce this. And that inequality, it looks more like hyperconductivity, but it has these penalty terms. So this T or F L4 norm is at most F L2 norm plus some error terms which depend on the derivatives. Okay, this is roughly the form. And then if your function is global, then you can somehow get from this form with error terms, and you can remove all the error terms. Okay, so I mean, doing this proof will be too long and nobody will be able to follow, but the proofs are really elementary if you do them right. It's a bit tricky to get the right statement, but then the proofs are easy. There are by now like 2 or 3 different proofs. The first proof that I saw was some proof by induction. Okay, like the proof that we've seen. You just need to figure out what is the statement that you want to prove by induction. And once you do it, then actually the proof is very simple. Okay, but it's a bit tricky to come up with the statement. And eventually you also need to do some reduction to the, I think, unbiased case. So this is proof number 1. Proof number 2 uses an exchange argument. So you take your function, you take the Fourier coefficients, and you construct a different function where you keep the Fourier coefficients, but you change the Fourier characters from the p-biased characters to the unbiased characters. If you think about it, it's something very strange to do. So you just keep the Fourier coefficients, but you change the basis. And then the claim is that if your function is global, then these two functions actually have similar behavior. And this you prove by changing the coordinates one by one. So like initially all the coordinates are p-biased, and in the end all of them are unbiased, and then there is one by one, and you keep track of the error, and everything just works out. Okay, so this is like a classical technique from probability theory, which is also used to prove this very SEN theorem and this invariance principle. Yeah, and I think there's also a third proof, but I don't remember. Anyway, we're not going to see any of that, but if you're very interested, you can ask me and I can show you the papers. Or you can look at my lecture notes. Okay, so questions about global hypercontractivity.
The square root of beta is height.
Yeah, so everything here is homogeneous. So if you multiply f by a constant, then this will be multiplied by a constant, and this will be multiplied by a constant, and this will also be multiplied by a constant. So it has to be, like you can ask whether instead of 1/2, 1/2, you can get something else. Possibly. Yeah, there are also statements where instead of 2 and 4, you have 2 and something else, like 2 and I think any even integer you can do. You can ask where there is a global log solver inequality, but nobody bothered to prove it. probably hasn't found uses so far. Yeah, so there's a lot of research about this hyperconductivity and global hyperconductivity, but the focus is on proving them for other domains. Yeah, because this is good enough for applications on the Boolean cube, so we don't need to improve it.
Could the beta be small for F being F with like some kind of pseudo-random property? Or
Yeah, so here, this is one example of the pseudo-random property, which will be useful for us. Yeah, so this is the way to think about it. So it's, I guess what we're actually going to show, so the proof of this Rogaine Wilfus theorem will show that beta has to be large. So this assumption that influence is small implies that F cannot be beta pseudo-random, beta global, sorry, for a very small beta. And the fact that it's not beta global for small beta will directly imply this boosting. So it's very simple. Yeah, so kind of if your function was pseudo-random, then it couldn't have had small influence, not all influence.
Also for me, it seems like the row should not be, the noise should not be 100%.
So that should be.
Noise should be not 100%. So row.
Yeah. So right. I mean, this law is positive. So it's like 1/5 or something. I don't remember exactly. So you can compute it.
So I can compute it out of beta. Or
No. It's independent of anything. It's just a constant, like 1/10.
So there, it is an absolute constant.
Right.
Does not depend on f squared time.
Does not depend on anything. Yeah, if you're willing to accept a constant dependent on p, then you don't need the globalness. But the point here is that this is independent of p. Because in the application, p is going to be dependent on n, but you want the end result to be independent of n. So you need some statement which does not depend on p.
Is there an estimate of row, known estimate of the row we are seeing
Of the
of the row? Because row is independent of any constant here. Do we have exact computation of the formula?
the optimal law, I don't think so. There is some law that comes out from the proof. If you look at the application, then this the value of rho is going to translate to some value of some constant somewhere. And usually we don't care about constants. Yeah, so I don't think anybody bothered to find the optimal value here or the optimal form of the right-hand side. But if you do it, then maybe it will find some applications. So I think there is some. So I mean, the way these things work, so the people working on this, they have very high standards. So they say, if what I'm doing cannot be published in Annals of Math, maybe I'm that dirty, jams, I'm not interested. So that's how they think, and it's only a few of them, so they have enough interesting problems to work on. So usually there's this army of students who just, they're just starting out, so they start by proving results which are not the level of jams. But because it's a new topic and it's not very accessible, I talk to these people, and I hear their talks over and over again, so I understand it by now a bit. But you are not exposed to it, so it's kind of without some guidance, there's no way that you're going to join the race. And I think for this reason, nobody bothered doing this lower hanging fruit. Okay, but there is some scope for doing it. Okay, so maybe it won't be as interesting as some other things, but it might be useful, and who knows. Yeah, other questions?
Can we compare the photonics with symmetric property?
What symmetric property?
Like every variables have the same influence.
Yeah, so here it doesn't help. Okay, so if all the variables have the same influence, it just means that okay, so first of all, it's not enough to look at individual variables because we need it for all the set S. But let's say that that you are going to graph property or whatever, then we just mean that in order to check this, it's only enough to check it on all isomorphism types. Okay, so this comes up when you're proving like Green-Tau type theorems. So the Green-Tau theorem, it finds arithmetic progressions of any length in the prime. And what they do is they construct a set of almost prime, where the prime is dense, and they show that this set of almost primes is pseudo-random, for whatever notion they need. Okay, and then they have a list of a few pseudo-random properties, and this makes it feasible to check them. Okay, so it's just a few pages of integrals, and they can show their pseudo-randomness. But here, at least in this application, this is not the case. In other applications, you do want to prove that specific functions are global, and then something else follows. So for example, characters of the symmetric group are global. And this implies some character bounds, which translates to something in extremal combinatorics. Okay, but it's not the case for us here. Yeah, so short answer, the symmetry doesn't help so much. Where symmetry does help, okay, so let's take a look at the KKL theorem. Okay, so there was always a variable whose influence is like log n over n if the function is roughly balanced. Now let's say that you knew that all the influences are the same. Yeah, so the total influence is at least log n. Okay, this means that the threshold is at least somewhat sharp because the derivative has to be at least log n in the critical window. Okay, so this is confusedly also called like the sharp threshold theorem of Friedgut and Kalai. It's a different notion of sharp threshold. Yeah, so this derivative is at least, so this would mean that the width of the window is always at most 1 over log n. And there you do use the fact that all the influences are the same. So if you know that at least one of them is large, and actually all of them are large. Yeah, any other question?
When we want to use the global hypothesis for any general f, can we split f into the two parts, the structure part and the stochastic part?
Right, so this is this regularity lemma. So what these regularity lemmas do is they construct some sort of decision tree. So they query some variables, and most of the leads will either be very close to constant or very pseudo-random, like beta global for small beta. And this is enough to, let's say, prove some results about intersecting families. And the idea is that if you look at two global families where they're not very, very sparse, then they will contain sets which are disjoint. This is what you need in these applications.
Very well, what's the keyword you were referring right now, right?
Yeah, this is a regularity lemma. This appears in papers of non-metrics with people like Alice and others. Yeah, if you're interested, and I can point you, there's a lot of literature, and the papers tend to be quite long, usually because they contain lots of results. Yeah, any more questions? We're not in a hurry, so. Okay, so what we're going to do now is we're going to prove to get the proof theorem, and hopefully I won't get confused. The proof theorem isn't so difficult. It's kind of similar to the proof of the KKL that we've seen, although we won't see influences. So in some senses it's similar, in other senses it's different. So this will be proof of Regan's theorem. Okay, so the assumptions are so the expectation of f under mu p. This is between 1/3 and 2/3. And we also assume that the influence with respect to mu p, the total influence of F, is at most some constant k. And like all of the order ones, omega ones, they will depend on k, but only on k. Okay, now. So this implies that it's at least 1/9. And this implies that if you look at this thing, this is 1/10. Okay, so we've seen that when we proved the KKL theorem. So this is like the influence is the like average size of a set in the Fourier expansion. So this is just Markov's inequality. Okay, and this is just because it's at least 1/3. Okay, and if you combine these two things, then what you get is that this is at least 1/9 minus 1/10 is 1/90. Okay, so this is like we did in the proof of the KKL theorem. Okay, so I want to look only at the low degree part of F. So this is also something that we did for the proof of the KKL theorem. Here the reason is going to be different. Okay, so this 10K is going to translate to the size of the booster in Bourgain's theorem. Okay, so this thing is we've also seen this. Okay, so we've seen this in the proof of the level D inequality, this calculation. And in the same proof, we also saw this. So this is Feldher's inequality. Okay, now because of the monotonicity of norms, then this is at most F2, which is at most 1, because F is 0, 1. Okay, so here we don't need to work hard, and this bound is going to be good enough for us. Okay, so what we got is that this thing is at least 1/90. Okay, and now we would like to apply this global hypercontractivity. Okay, so yeah, so we had, so I'm going to square everything. So 1/90 squared is at most this F at most 10K 4 squared. Okay, and in order to apply this global hypercontractivity, then I do the same thing that I did when proving the low degree functions are reasonable. So I'm going to apply the node operator and its inverse. So this is, so I'm taking the same law as in the global hypercontractivity. So T rho minus 1 F at most 10K more squared. And this is at most this beta, which is the best beta. Yeah, I'm going to write the formula for beta soon. Times T rho minus 1 F at most 10K 2 squared. Okay, so I'm going to need this. Okay, where beta is the maximum over all S of DST or inverse F at most 10K 2. Okay, so I'm just applying this global hypercontractivity. Okay, now this T rho inverse F at most 10K 2, so I guess there's no square. So this is another computation that we've already seen, so I'm not going to repeat it, but because this function is low degree, then this has the effect of increasing everything by its most rho to the minus 10K. Okay. So this is most rho to the minus 10K. And consequently, beta is at least rho to the 10K over 90 squared. Okay, so we did all of this calculation. It's really very similar to what we've seen. So if you've seen this proof of KKL, the way that I wrote it, which is maybe not the way that it appears in the books, then you just essentially do the same thing, and you want to do some kind of reduction to global hypercontractivity. So given that you know that this is what you're trying to do, so far it's just kind of the proof writes itself. And it's going to continue like this. I mean, the proof is just going to write itself. It's very easy in hindsight. Like if you know the right lemmas that you're supposed to use, then the proof writes itself. Yeah. So we would wish that all the proofs were like this. Okay, so this is what I promised to you. So the only way in which the total influence can be constant is if the function is not global. But not the function itself, but well, this T-rho inverse. But this T-rho inverse is not going to make too much of a fuss. Okay, so this implies that there exists S such that ES T-rho inverse F and K 2 squared is at least, yeah, let's not take the square right now, is at least rho to the 10K over 90 squared. Yeah, so spoiler, this S is going to be the booster. It's not surprising. Okay. Now I want to say some things about S. So because this function has degree 10K at most, if S is larger than at 10K, then this thing is 0. Okay, so observe size of S is at most 10K. And also I want to get rid of this T-rho inverse. And I do it in the same way as here. Okay, so there are maybe some details, but so 10K over 90 squared. So this is at most this ds T-rho inverse F most 10K, which is at most rho to the minus 10K ds at 10K. Okay, and now I can get rid of this 10K. Okay, so if you recall, so this this ds, it takes part of the Fourier expansion and it removes some stuff from it. Okay, so this is like the sum of all the Fourier coefficients of f, which contain s, and f size is most 10K. So if I remove this at most 10K, then this only increases my norm. So this is at most O to the minus 10K ds F2. Okay, so now I'm going to move this here. And I'm going to square everything. And my final result is this way. So O to the 40K. So I get 40 because I'm squaring everything. Over 90 to the 4. So this is at most DSF to where is DSF squared. Okay. So now, what is DSF? So DSF is this kind of inclusion exclusion. Okay. So at every single x, the value of DSF is at most 2 to the size of f. Okay, it's even 2 to the size of s minus 1. Okay, also we know that if this value is equal to this value, and actually all of them have to be equal, and this entire thing is 0. Okay, so this DSF is only non-zero if they are different. So this is at most 4 to the side of s, the probability that f s1 is larger than f or s0. It's 0, 1, so it means that this is 0 and this is 1. Okay, and this is at most 4 to the 10K. Okay, so what you eventually get, you get that the probability f s1 is 1 and f s0 is 0 is at least all to the 40K over 90 to the 4, 4 to the 10K. Yeah, which is something which is exponential in K. Yeah, now we're basically done. So the probability that when you feed f s1 minus the probability of new field f equals 1 is at least the probability that f restricted to s is 0 times the probability that Okay, so here I'm going to use the fact that this E is little of 1. So this is 1 minus little of 1 times this mess, times some alpha to the k, where this alpha is some universal constant. Constant. Yeah, and this is what I promised, this boost in the probability. Okay, so this failure of globalness, it's the same as boosting. It's really the same, roughly speaking. So because this set S is small, then usually the coordinates there are 0. So up to this factor of 4 to the 10k, then the boosting probability is exactly this globalness parameter. Yeah, so like I said, the proof writes itself.
We don't even need volatility for the full domain, but only for S. Right.
Well, we use monotonicity, for example, when proving the Filmus formula. Yeah, but it's pretty, you can probably get out of this sum statement, which is also works when you're not monotone. But in general, you can't expect this type of boosting. Yeah, because maybe you take 1 minute seven. And so this result, I guess it was considered to be a hard theorem, but as you can see, the proof is like, it's very simple if you do it correctly. Questions? So here the boosting is exponentially small in k, and you can ask whether this is optimal, and I guess the answer should be yes, but I don't remember the example. Yeah, now in principle, we do care about these constants. So for these people who ask about constants, so I think from this you might be able to get things like for connectivity, the length of the threshold window is smaller by a factor of constant times log n. With this constant, it depends on the constant floating around here. So if you wanted to get this constant right, then you need to improve these constants along the proof. So there's some reason to try to improve the constant. It probably won't help you anyway to get the right constant, but still.
We have the symmetrical version of building boosters. Yeah.
Well, but it's you don't get anything. So you just means that this S you can put it anywhere in your. But I don't think it gives you anything. So I mean, you can ask, what am I trying to get? So let's say your probability is containing 10 triangles. So if you put one triangle, then you boost your probability. But so what other statement do you want? So you can add any triangle and boost your probability, but this just follows from the symmetry without doing anything in the proof. So what this symmetry could buy you is like this Boolean line that explained. So if you know that one influence is large, then all influences are large. So this is one way to actually use it. In this Boolean result, then they need to know something about the symmetry group, and this somehow translates to some improved bound on the maximal influence. So instead of like log n over n, they get maybe log n log n over n or log n squared over n. Depending on some quantity related to the permutation means. So they use symmetry in some way, but nobody understands their proof. And also, I think some of the calculations there are wrong. So maybe the theorem is correct, but the application is wrong. So yeah, so they do find a way to use the symmetry somehow, but here I'm not sure. Yeah, I guess you can do the calculation and see that you do get this exponential dependence. So the most you can hope for is improving some constants if you use symmetry. Okay, other question?
We have a global reverse.
Yeah, so reverse hyperconductivity actually holds also for small p, I think. So this is another property which holds regardless of p. So we don't need any special version, if I recall correctly.
By reverse, you mean we can remove the omega portion of output.
So reverse hyperconductivity is this inequality which looks like hyperconductivity, but the values of p are at most 1, and the inequality is in the other direction. And that's why it's called reverse hyperconductivity. It implies this thing that if you have two sets in the cube and you do this random walk which corresponds to the noise operator, then it gives you a lower bound on starting at one and hitting the other. Yeah, that's maybe the way that it's used. And in the Markov chain world, it's equivalent to this modified log Sobolev inequality, which in the discrete world is weaker than log Sobolev, but in the continuous setting is equivalent because of some integration by parts that you can do in the continuous setting, but not in the discrete setting. Anyway. Okay, so in the final bit less than half hour or so, I would like to do something which is hopefully simpler. So we're going to present a proof of the Erdős-Korolyi theorem using p-bias Fourier analysis. And it's going to be very simple. And maybe it's not as simple as this cut in a circle proof, but still quite simple. So now you can forget about everything, and we focus on the Erdős-Korolyi theorem. Well, the theorem, I start by taking it. Okay, so this is the p-bias version of the Erdős-Korolyi theorem. Okay, so let P be strictly smaller than half. But if F is intersecting, so this means that any two sets in F intersect, then mu P of F is equals P with equality if and only if F is star. So all sets containing a fixed element. Okay, so if you've seen the Erdős-Karolyai theorem before, then usually it's stated in the K-uniform setting. Okay, so you have K which is less than L over 2, and you have an intersecting family of sets of size exactly K. And then it's size with at most N minus 1 choose K minus 1 with equality if and only if it's a star. So this is the p-bias version. Okay. This is weaker than the uniform version in the sense that you can actually derive this from the uniform version, maybe up to this equality, and not the other way around. But you can sort of take the proof that you're going to see now, and you can also do it in the uniform setting, but it's a lot more painful. Okay, the original proof, I'm not even sure. You can prove it using the Kutzal-Katonas theorem, or you can prove it using this Katonas circle argument, which is very elegant. And we give this Fourier proof, which has some advantages that you can easily prove stability. So if the measure is very close to p, then your function is very close to a star. And the idea is we're going to find a distribution x, y on pairs of disjoint set. Okay, so I'm identifying elements of 0, 1 to the n with sets such that x, like the marginals look like mu p, and use expression of f of x of y equal to 0, where f is the characteristic function of the family. Okay, and f of x, f of y is equal to 0 because it's an intersecting family. So if you take any two disjoint sets, then it cannot contain both. Okay, so this is the idea. And now we'll see how to implement this idea. Okay, so we will take x will be just sampled according to mu p, and y will be sampled according to n rho of x, which, if you recall, is for every coordinate, we keep it with probability rho, and we resample it with probability 1 over rho. Okay, and we want the probability that xi equal yi equal to 1, we want this to be 0. Then this will ensure that the two sets are disjoint. Okay, now we can compute this probability. So the probability that xi is equal to yi equal to 1. Okay, so this is, first we need xi to be equal to 1. So this happens with probability p. And then either we just copy it. So this happens with probability rho. Or we resample it. And then the resample has to be equal to p, to 1. Okay, so we want this to be equal to 0. And I'm sorry, it's a bit confusing that the rho and the p look similar. So maybe it's a poor choice of notation. Okay, so maybe somebody here is quick and can tell me, okay, so this is equal to p plus 1 minus p rho. So which value of rho makes this 0? Okay, so we need p plus 1 minus p times rho to be equal to 0.
Minus p.
Minus p over 1 minus p. So we take rho to be equal to minus p over 1 minus p. Okay, so this is a negative probability, but this is okay. Okay, so this T rho operator, okay, maybe this doesn't really make sense, but I mean, this is going to correspond to this T rho operator, and this is the T rho operator is defined for whatever rho. So we just, you know, we ignore the fact that this is negative and we just go forward. Okay, so now we think about it, that this expectation of f of x, f of y, this is exactly the inner product of f with T rho of f. Okay, because how is this inner product defined? So first we sample x. Yeah, and this is the expectation of f of x, T rho f of x. And then T rho f of x itself is sampled by taking y according to n rho of x. Okay, so it's the same distribution. Okay, and like we said, this thing is equal to 0. Okay, now we have a formula for this. Okay, so this is the sum. Now we apply the two-function version of Parseval. F hat of s, 0 f hat of s is sum of s, well, s f hat of s squared. Okay, now we're going to split the sum into two parts. Okay, so this is, we take the empty set, so we get f hat of empty set plus sum over s different from empty set. We'll see in a moment why we're doing it. So maybe you don't see it yet, but the proof is almost done. Okay, so now we observe that because p is less than half, then this rho is between -1 and 0. Okay, so it's negative, but it's larger than -1. Okay, and actually this part of the proof would work even if p is equal to half, and then this rho is at least -1. Okay, and this means that if I look at these, we call them eigenvalue. Okay, so I start at rho, which is some negative number, then rho squared is positive, and then rho cubed is again negative, but it's smaller in magnitude. And so we continue this way. So this means that the most negative that this eigenvalue can be is rho. Okay, so this is at least f hat squared plus rho times okay. Now, what is this? What is f hat of the empty set? Right. So in order to be somewhat less confused, so I will add one more piece of notation. So we will write mu p of f. Well, we'll call this mu. Okay, so this is mu squared. And what do we have here? So if we summed over everything, then we would get the expectation of f squared, which is the same as the expectation of f, which is also mu. Okay, so this is mu minus mu squared. Okay, which is mu times mu plus log 1 minus mu. Okay, and this is at most 0. Okay, so we get that mu. Now I'm going to substitute the value of log. Okay, so I'm going to do some algebra. Okay, yeah, this is the difficult part. So, yeah, what we should be getting is that mu is at most p. If we do the algebra. Okay, so it's mu minus p mu minus p plus p mu is at most 0. Yeah, this is the Avogadro theorem. Yes, I don't know if you like this proof. We'll see in a moment if you can get a bit more out of it. But this is the Fourier proof of Avogadro theorem. It's also really the proof using the Hoffman bound, the Lova's theta function, degree through sum of squares, and blah, blah, blah. So there are other ways of describing this proof. But if you want, you can think of it as the Fourier proof of p-biased Avogadro theorem. Yeah, now we're going to see the advantages of this kind of proof. Okay, so this just gave us the upper bound, but actually in the statement which is hiding in this board, I promised characterization of the extremal cases. And we're going to get it very easily from this proof. This is not so easy to do some of the other proofs. Okay, so if mu is equal to p, then all inequalities are tight in the proof. Right, so the only way that mu is equal to p is if all the inequalities that we have here were tight. But actually, we only have one inequality. Okay, it's this inequality. Then for this inequality to be tight, then we need that f hat s squared can only be non-zero if the size of s is 0 or 1. Right? Otherwise, this inequality would be loose. Okay. Okay, this means that the degree of f is at most 1. Yeah, now you can ask which Boolean functions have degree 1. And I'm not going to do the proof, but it's really it's very simple. It's really very, very simple. So the only functions which have Boolean functions which have degree 1 are 0, 1, xi, and 1 minus xi. This is a really easy exercise. So can encourage you to do it. It's like I can do it, but I prefer doing something else in the remaining minutes. Okay, and of these functions, the only one which is intersecting is xi. Okay, so this proves the uniqueness in the Erdős-Kovács theorem. So the only extremal families are these xi, which correspond to these stars. And they also have other names. But we can do more. So if mu is close to p, then the inequalities were almost tight. Okay, so now it's not true that all of the Fourier mass is on levels 0 and 1, so on coefficients of size 0 and 1, but almost all of it. Okay, so this implies that F1 is small. So let's say it's this P minus epsilon. So you can do the calculation and you can get that it's order epsilon. Okay, so this is again an exercise given what we saw. It's not difficult. Okay, and now we apply this result, the FKN theorem, which is the second paper in Boolean function analysis ever. Okay, so the original application wasn't the Erdős-Kovács theorem, it was something else, but ever. So for constant p, this implies that f is other. There exists g, this form 0, 1, xi, 1 minus xi, such that the probability that f is different from g is order epsilon. Okay, which means that your intersecting family is close to the star. There's some star which is very close to your family. Actually, using other stuff in Boolean functions, I think you can get a better exponent. And this has been worked out and by Malnifit and maybe Nathan Keller in some paper. Okay, but really the advantage of these Fourier techniques is that they work not only in characterizing the unique cases, but also in characterizing stability. So many results in Boolean function analysis, I mean, we haven't seen actually any of them, but many of them are these structural theorems, which they say that if your function almost satisfies something, then it almost has some structure. And this is kind of, it comes naturally out of the Fourier setup, where we think of everything in terms of these Fourier coefficients, and well, this allows us to do these quantitative arguments. Okay, so this may be one reason why this Fourier analysis is useful for experimental combinatorics, because it allowed us to prove these stability results. Okay, so this FKN theorem, so this stands for Friedrich, Kalai, and O, so the proofs aren't trivial, but some of them are better. This more or less follows from the central limit theorem. So yeah, I don't want to spend the time, but you can come ask me later if you want. Yeah, but once you proved it, then it kind of implies the stability, and not only in this situation, but in any other situation where you can prove this kind of statement. So if you have some other intersecting theorem where you are able to prove this kind of bound, then you immediately get approximation by a star, for example. So as another example, let's take triangle intersecting families of graphs. Okay, so it's a collection of graphs on n vertices, the same n vertices. And if you look at the intersection of any two of them, then the intersection contains a triangle. So such a family contains at most 1/8 of the graphs. Okay, and the only way for it to contain exactly 1/8 is to be all the graphs containing a fixed triangle. And if your measure is almost 1/8, then you must be close to one of these extremal families. Okay, and you can do a similar type of proof. I mean, it's more complicated, but the proof will show that, yeah, so the first thing would be some calculation like this, but more complicated, which would say that mu is at least 1/8. And then for uniqueness, then you get that the degree of f is at most 3. And this will imply that you have to be, this everything that contains the fixed triangle. And if your measure is almost 1/8, then you will be close to degree 3 in this kind of sense. And then you apply the degree 3 generalization of FKN due to Kinda and Safla. And you get that you're close to an extremal family. So you just follow the same kind of steps and you get similar results. And this works in many other situations as well. So I think the easiest way to characterize the extremal intersecting families of permutations is using this kind of approach. Otherwise, it's a not very nice combinatoric.
Because people consider, so I have two questions. One question is, when we do the uniform setting, where you say you have a uniform intersecting.
Yeah, you can do it. What's really happening here? We're computing this Hoffman bound level theta function, so you can do it, and you'll get the same thing. So now it's possible in this setting to talk about the mass on different levels. Okay, this comes out of the association scheme, the Johnson association scheme. So you can talk about degrees and everything. So you will get that you'll get your upper bound, and if you have size exactly k over n, then you have to have degree 1, which would imply that you have to be a star. And if you're close to degree 1, then you can apply a version of this FKN theorem to this setting, and it will show that you're close to a star. So you can do it. And actually, there's a paper of Funkel and Graham where they prove the Edwards coordinate theorem this way. It's called all the new proofs of the Edwards coordinate theorem. There's many proofs, and this is one of them.
And can we also do Hilton Miller?
Yeah, this I haven't seen. So in some of these papers of Lifshitz, Keller, and Ellis and their friends, then they in some other situations they prove similar results. So I mean, you can sort of get it, and then to get exactly Hilton Miller, you will need to use some bootstrapping argument that will tell you that somehow you use regularity or whatever to get into this situation where you almost look like a Hilton Miller family. And once you know this, you can do some calculation to show that you have to be equal to the Hilton Miller family. So there's additional bootstrapping stuff. The Hilton Miller asks what is the maximum size given that I'm not a subset of stuff. Yes, if you want to know more, there's a book of Ryan O'Donnell called Analysis of Boolean Functions. It's very long and it contains everything up to that moment. You can look at lecture notes by myself, by Noam Lifshitz, Hamid Khatami, and so on. And if you're interested in something specific, send me an email. I might reply.